Hello. In part 1 of this series I started to tear down this Rode und Schwarz frequency meter built in 1962. Besides making space for more useful things, my main goal was to salvage many old school high quality components in order to build a vacuum tube tester or even a whole testing environment, which will enable me to do extensive experiments with vacuum tubes, as well as to repair vacuum tube-based devices like old amplifiers and radios. So, to those of you who didn't like the idea of disassembling something rare and beautiful like this, be aware that this sacrifice will help in creating and saving many other rare and beautiful things. Since we still have the guts of several unopened modules to discover, I decided to do the following. All consecutive parts of this series will include a teardown of one of the modules. After that, explanations of the basics of vacuum tubes and other old-school electronics, as well as the construction of the vacuum tube testing environment, will be the subject of the videos. In this part, I will tear down this module. Then I will build a special type of high-voltage generator for the vacuum tube tester. Part of that will be a thorough explanation of its working principle. So let's get started. Here is a view of the inside of the unit. As you can see, I have already salvaged some components. I can't show you that though because the video material was accidentally deleted. As you can see, the enclosure is compartmentalized in many smaller sections which include various circuits. Some components are soldered to these brown boards, which are called solder tag strips. You can find these often in 50s and 60s equipment. Other components are soldered to these insulating ceramic mounting posts. Other mounting posts are directly riveted to the enclosure. All shields are silver plated on the inside, just as well as on the outside, shielding the circuits from external fields as well as from each other. What we also see is a range of adjustable coils. Some of the coils are wound from ordinary copper magnet wire, while others are made from silver-based magnet wire. To take them off, an aluminium tube that certainly acts as a shield has first to be unscrewed, freeing the view on a little brass screw that can be turned to change the position of a little ferrite core inside the coil. This is done in order to adjust the inductance of the coil. The screw is made of brass because, other than an ordinary steel screw, this screw has no ferromagnetic properties and has a very low magnetic permeability, similar to the surrounding air. Normally, adjustable inductors for RF applications are trimmed by a plastic rod rather than with a screwdriver for that exact reason. In this case, using a steel screwdriver would however be less of a problem because of the brass between its tip and the ferrite. Let me now make some measurements in order to demonstrate the change in the coil's inductance that I can cause by turning the screw. For the first measurement, the ferrite core is completely immersed inside the coil. The LCR meter reads an inductance of 2.6 microhenries, which equals 2600 nanohenries. By turning the screw to the left, I now pull the ferrite core out, so that it is now completely outside the windings of the coil. The inductance of the coil has now dropped to a value of 0.7 microhenries or 700 nanohenries. If you want to understand why this happens, watch my SMPS tutorial part 5, in which the basics of magnetic circuits are explained. The next remarkable thing is a group of small wire-wound trimmer potentiometers or rheostats, which were made by Rosenthal. The Rosenthal Corporation is today better known for the production of high-quality porcelain products like tableware, but they also used to manufacture power resistors, rheostats and ceramic insulators. After removing nearly all electronic components from the enclosure, what remains is the next oddity: two rotary switches which are coupled together via a chain drive. These switches could still be sold for some money, but I guess I will keep them for future projects. The silver-plated enclosure itself will of course not be thrown away. I will later try to remove the tarnish from its surface by using a refined version of the method which I have shown you in another video a few days ago. If you would simply mount an aluminium sheet on top, you could easily close the enclosure and reuse it for all kinds of RF projects. The very high shielding capabilities would also possibly make this a candidate for EMP-proof devices. But there is more. On top of the enclosure, two small shielded boxes were to be found. After removing the cover, some more interesting components are revealed. The circuits inside these boxes are no doubt some kind of LC filters. These are again adjustable inductors. This is a more typical example though, where we have no brass screw, but a threaded ferrite core that can be screwed in or out, preferably with a plastic rod, as I have mentioned before. These coils are somewhat similar to the ones I used about 1.5 years ago in my RFID projects. Again rare, but useful components that are quite hard to come by. Inside the other box are, again, inductors of yet another design. The winding is actually partially encapsulated inside the ferrite core. This core shape is called a pot core. And it is quite similar to these RM6 ferrite cores, which I just bought the other day to make storage chokes for miniaturized switching converters. It's interesting to see that not really much seems to have changed in 50 years when it comes to the design of inductive components. So, after taking a closer look at some parts, let's get an overview over all reusable components that I could score so far. Some vacuum tubes, tube sockets and shields, some nice old plastic knobs, a couple of very useful solder tag strips, one of which we will need later in this video. Compared to a modern PCB, they might seem useless at first glimpse, but they are really useful for experimental circuits, especially in RF and high voltage applications. And then of course the adjustable inductors. As said before, some with copper and others with silver windings. And then a pair of really beautiful old school neon lamps. One of them combined with a rather interesting main switch of the device. Then of course the meters, the rheostats, and our pair of rotary switches. And last but not least, an assortment of Bosh brand metallized paper capacitors, which, at least in Germany, are recognizable by the two letters MP. These are the first components that will be reused in our project. And better yet, it's going to happen today. By the way, the large capacitors which we saw inside the power supply unit in part 1 were not, as I thought, electrolytics. They too were metallized paper capacitors. In fact, I did not find a single electrolytic capacitor in the device as of now. That, however, is a good thing, since MP capacitors have some advantages over electrolytics. They are, for example, non-polarized, which makes them more versatile. But so much for the teardown. Let's come to our actual project. The power supply, which I salvaged from the frequency meter in part 1, is able to deliver two output voltages of up to 350 volts DC. By connecting the filter capacitors in series, even 700 volts DC could be reached. In order to carry out certain experiments on vacuum tubes and other gas-filled tubes, I will however need even higher DC voltages. To generate these voltages, I decided to build a voltage multiplier cascade from the capacitors I found inside the unit. This circuit, that is also known as a Cockcroft-Walton generator, works in the following way. First, we have a simple half-wave rectifier, consisting of a voltage source, a single ideal diode and a capacitor. The ideal nature of the diode includes that it has no forward bias. The voltage source supplies a sinusoidal AC voltage, similar to what the power grid delivers, as can be seen in the graph on the right-hand side. For t equals 0, that is before any charges have moved to the capacitor's electrodes, the voltage across the capacitor is 0 volts. But as time progresses, the capacitor is charged via the diode and the voltage across it approaches the value of the effective or RMS value of the AC supply voltage times the square root of 2. In theory, this value is only reached after an infinite amount of time, but 99.9% of that value are reached rather quickly in any practical application, making the difference to the ideal value negligible. From a theoretical standpoint, it must also be mentioned that, strictly speaking, this only works when a series resistor exists in the circuit that comprises a series RC circuit with a capacitor. In reality, this is always provided by the internal resistance of the source, the ESR of the capacitor, and the wire resistance of the connections. For the sake of simplification, these resistors are not visible in the schematic. But in order to understand why, you would have to learn about differential equations and transients, which exceeds the limits of this video. For all practical purposes, it is enough to know that the capacitor is charged over time to a value of roughly the RMS source voltage times the square root of 2. For example, if this circuit would be directly connected to an electric outlet in a 230 volt grid, the capacitor would be charged to a value of around 325 volts DC. Now let's use Kirchhoff's voltage law to set up a mesh equation for this simple circuit. That equation would be Vs minus Vd1 plus Vc1 equals 0, from which follows that Vd1 equals Vs plus Vc1. This means in spoken text that once C1 is charged up, the voltage across the diode D1 is the source voltage plus the DC offset provided by C1, as can be seen in the graph on the right hand side. The voltage across the diode alternates between 0 volts and 2 times Vs times the square root of 2, which would equal to 650 volts DC when powered from a 230 volt grid. If we now redraw the half-wave rectifier circuit and add another half-wave rectifier, we can use the voltage across D1 to charge a second capacitor C2 to that peak voltage of 2 times Vs times the square root of 2. In this way, the voltage across D1 acts as the voltage source for the second circuit, and C2 charges up to twice the peak value delivered by the actual AC voltage source. We now have what is called an asymmetrical voltage doubler. This idea, however, is not restricted to a single circuit, but can theoretically be repeated and cascaded as often as needed to reach a certain output voltage. Here we have two cascaded voltage doublers forming what I call a two-stage multiplier cascade. The circuit diagram of a cascade is then often redrawn in this way. Limited by the number of capacitors I found inside the frequency meter, I will build a four-stage cascade later in this video. The output voltage of such a circuit is roughly 8 times the peak value of the AC input voltage. Important for the design process is that only the first capacitor is charged to the simple peak voltage, while all other capacitors are charged to 2 times the peak voltage. This is both true for the upper and lower row of capacitors. In my actual implementation of the circuit, I will therefore have to create 3 pairs of capacitors which will be connected in series in order to double their rated voltage. The actual values of the available capacitors are the following. 1 4 microfarad 300 volts capacitor, followed by 3 5 microfarad 500 volt capacitors, which I have additionally salvaged from old dishwasher motors. In the lower row, we will have 3 pairs of 8 microfarads 300 volts capacitors, each comprising a 4 microfarads 600 volts capacitor. The last capacitor in the row is rated for 4 microfarads at 630 volts. The peak voltage is limited by the capacitors to 250 volts DC. Therefore, 2 kilovolts will be the absolute maximum output voltage. I do, however, believe that though exceeding the ratings, 2.4 kilovolts of output voltage would be technically possible. If we now write down the potentials at the different nodes inside the circuit, we can see that the diodes must be able to handle at least 250 volts of reverse voltage. The diodes that I will use are of the N1-5408 type. Furthermore, a voltage divider will have to be added in order to measure the actual output voltage. 2.4 kilovolts exceeds the measuring range of any meter I own. But enough theory for now. Let's start to build the cascade. These metal sockets are used to hold the capacitors in place. I turn them around because I will mount the capacitors upside down with their pins pointing upwards. For that I also cut out a wooden base plate which also needs some mounting holes in order to bolt the capacitors to the plate. I choose wood rather than aluminium because I want to insulate this entire module from the rest of the device. I don't want to provide a conductive path between 2 points of large potential difference via the metal cans as I would when metal would be used as a base material. As I mentioned before, the capacitors from the frequency meter are supplemented with 2 similar capacitors which I salvaged from old dishwashers. I've got to work with what I have. Now all capacitors are mounted on the base plate. I arranged them according to the layout of the circuit diagram. That is of course not necessary from a scientific standpoint, but it makes sense from a safety standpoint always to know which component is which and where certain dangerous voltages are to be expected. The little labels on the capacitors serve the same purpose. The capacitors are then connected with copper wire bridges. After that, the diodes are soldered in place. The cascade itself is already finished, but we still need a voltage divider to measure the output voltage. For that, I first have to make some basic calculations. I start with components which I already own. I have a lot of resistors lying around, but most of them share common limitations. They are rated for a maximum voltage drop of 250 volts and a maximum power dissipation of 0.25 watts. Since the maximum output voltage of the cascade is 2.4 kV, at least 10 resistors of identical resistance will have to be connected in series so that the first limitation is not exceeded. 10 identical series resistors would then be able to dissipate an overall amount of 2.5 watts. So from the equation P equals V squared over R, I can derive that the minimum resistance of the entire divider must be 2.304 megaohms. My solution is to connect 10 1 megaohm resistors in series and then add another 10 kiloohm resistor across which a voltage can be measured. The division factor of the voltage divider can be calculated by the voltage divider equation. The result is that the factor will be 1 over 1001. Ideal would of course be a factor of exactly 1 over 1000. But since these resistors have a large tolerance of 5% anyways, that difference plays no role. The measurement will only be a rough figure and not a precision measurement. But it will be accurate enough for all that I want to accomplish. So let's build the divider. As a base, I use one of the solder tag strips which I salvaged from the frequency meter. I solder all resistors onto it. Mount the strip on the wooden plate and connect the cascade via copper wires to the divider. Now the cascade is ready to be tested. My variable isolation transformer serves as the voltage source. The left DMM displays the RMS value of the AC input voltage, while the right DMM measures the DC output voltage. For the first test, I will adjust the input voltage in such a way that the output reaches around 240 volts DC, meaning 1/10 of the maximum output voltage. I will then measure the voltage directly with the right DMM and see if the calculations hold up. After that, I will step the output voltage up to 1 kV and then 2 kV. So let's start the test. The values are as expected, around 30 volts, 60 volts, 90 volts, 120 volts, 150 volts, 180 and 240 volts. If you multiply these values by 10, you get the potentials that I had written down on the circuit diagram. Now I connect the meter to the voltage divider and reset the measuring range. We measure 245 millivolts, which is exactly 1/1000th of the actual output voltage. Now I crank up the output voltage to 1 kilovolts. If you sum these values up, you come to a value of around 990 volts, which is close enough to the expected value. The individual values, however, deviated quite a bit from the expected values, partially as much as 20 volts. One reason more not to go any further than 2 kilovolts output voltage. Now I step up the output voltage to roughly 2 kV or 2 volts across the 10k ohm resistor in the voltage divider, and I measure again. The sum of the measured values equals roughly 2010 volts. Okay, now that I know that the cascade works as expected, I have all I need to perform an experiment that I have come up with to explain the basic principles behind vacuum tubes. But more about that, and of course some more teardowns, in the next episode of this series. I hope you enjoyed this video, and I hope to see you next time as well.